My name is Nick. I'm a PhD student here. I'm working in nuclear medicine. At the beginning of this little seminar on antimatter, you were told that antimatter is actually not that strange, and we actually do see it in the world all the time. From the last couple talks, that might not seem apparent, which is why I think I've been brought in to show you some of the stuff that we do in the everyday world with normal people that involves antimatter. So, like I said, I work in nuclear medicine, and specifically I work with PET scans. So PET stands for Positron Emission Tomography. And as we've learned already, positrons are just the antimatter equivalent of the electron. And we're actually able to use this antimatter for medical purposes, so we can do actual scans. So this is a cancer scan, where this guy has a fair number of tumors here. I'm not a medical doctor, so I'm going to gloss over all the medical facts, so don't hold me to any of them, please. So what we do in positron emission tomography is we take an atom and we make it radioactive. We make it emit antimatter. We can do that with accelerators or with reactors. We do it in various ways, but the end result is that this unstable atom emits a particle of antimatter. It emits that positron. So that positron, as we were seeing earlier, very quickly meets an electron. They annihilate, their mass turns into energy, and they give off, that energy is given off in the form of two rays of light. But these rays of light are given off in a very particular way. They're at 180 degrees from each other, and they're always that way. And that allows us to do some fun stuff trying to detect them. So in PET scans, what we want is, we want this radioactive atom, emits this antimatter, the antimatter annihilates and turns into these two rays of light. And like I said, they go 180 degrees from each other, they go in opposite directions. So if you have detectors that are sensitive to these rays of light, and you have a whole ring of those detectors, then if you make a detection here and a detection here, you just draw a straight line between that, and you know that that antimatter was somewhere along that line. So that allows us to do some interesting things. So if you have enough of these radioactive atoms, enough of this antimatter in a particular location, then you'll get one annihilation and you get this line, and you know that something occurred on that line. Then you get another line and another line, and if you have enough of these things, you can build up statistics with a computer. That's the tomography part. And you're able to say, yeah, listen, that's where all of your antimatter was. So by doing this, by having these ring of detectors like that, we're able to get the position of where antimatter is. So I'm just going to mention another technique quickly because it's very similar and it'll come into play a little bit later. So with PET, you get these two rays of light and you need a ring detector. There's another technique called SPECT where you have a radioactive atom and it just gives off one ray of light at a time. But you can detect that, and all you really need to do is take your camera and what's usually done is you spin your camera around whatever is giving off those rays of light, and then you can kind of triangulate where that stuff's coming from. But it's the same idea, essentially. So there's a PET scan, like I said, a nice ring of detectors. This person has been injected with these antimatter emitters, and they're going to use the PET scanner to look at where those antimatters are. There's a SPECT camera. This thing is on sort of a rotating big gantry. And it's the same kind of idea, you just look at where that signal is coming from. So yeah, that's SPECT. You can use a couple cameras at a time and you're looking at the rays of light giving off these radioactive atoms. And this is an example of a SPECT scan, and I'll go back to this in a little bit. So what I've explained so far is that we've got PET/SPECT scans that allow us to locate a radioactive atom or a particle of antimatter. But we don't actually, especially in medicine, we don't really care that much about these radioactive atoms. We don't care much about antimatter. What we care about are processes in the body. But we can do something with this. So what we can do is we can take these radioactive atoms that we can track through the body and use them as tracers on atoms or on molecules that we actually care about. So one thing that's done a lot with PET scans is we use sugar. As a matter of fact, there are over 2 million PET scans a year in the US done with a radioactive version of sugar. So essentially you make this, this unstable atom that will emit the positron. You do some chemistry, we do some of it here at TRIUMF, and you attach that tracer onto a sugar molecule. And then you can inject this into a patient, and the sugar will go through the body the way normal sugar does, except now you can trace literally every molecule of that sugar, which is kind of interesting, because there's a particular kind of cell that really likes sugar. It's a cancer cell. So this is an actual PET scan of a patient with cancer. So everything that's lighting up yellow is where more sugar is going. The brain is lighting up because he's sitting there in a PET scan thinking, what the heck am I doing here? The heart is lit up because it's beating pretty quickly. And then there's a lump over here. So that's a tumor, that's a cancer, a lump of cancer, where those cells are dividing a lot more than they should, they're growing a lot more than they should, they're using a lot more energy than the tissue around them, so they're using more sugar. So when we've injected this guy with radioactive sugar, a lot of it goes to that tumor. And that's one way to diagnose cancer. Actually, it's a common way. But we can, because what we're tracking is just that radioactive atom, we can actually track more than just sugar. We can track a whole range of molecules that the body uses. So one thing that researchers are doing here at TRIUMF and all over the place really is looking at different brain chemicals. So you folks may have heard of dopamine and serotonin, things like that, happy chemicals, neurotransmitters that are used in the brain. They help regulate everything from mood to motor skills and things like that. So there's a whole dopamine system with a whole bunch of different molecules involved in it. And what we can do is we can actually put radioactive tracers on each of these molecules. So we can look at what's going on in people's brains. So here are an example of a couple PET scans. So I start off with this one. This is just regular sugar, and it's going to where there are tumors in this guy's body. There's also a spot down here that you may notice. That's the bladder. This guy will have to relieve himself soon. But we can also study brain diseases using PET scans. So again, this is just with the glucose analog, but the brain has sugar going through it naturally, normally. But with Alzheimer's disease, the same kind of injection doesn't correspond to the same kind of distribution in the brain. So some researchers are using this to study Alzheimer's, to study the progression of the disease, and to stage the disease. We can also look at the brain using dopamine analogs. Here we're studying Parkinson's disease. So dopamine is involved, like I said, in motor skills. And you can clearly see the difference between a normal brain and a brain of a patient with Parkinson's. And that's looking at where dopamine is going and where it's being used in the brain. So clear difference there. One interesting thing about this though is that we are tracing these different radioactive atoms. Using PET and SPECT, you can track a whole range of different atoms. And this particular image is actually a 5-modal image. So they're actually tracing 4 different radioactive tracers plus X-rays. So the X-rays give you the structure of the body. This is a mouse, in case it wasn't clear. It's not a person. Yeah, not a person. So this is a mouse. So the structure is given by the X-rays, and then we use a PET isotope to look at FDG, to look at the where sugar is going, and that tells you something about the metabolism, what parts of the body are using energy. We're also using indium and a couple other isotopes that are designed to help diagnose and help study different types of diseases, because these different isotopes will go to different regions of the body. So I like that image, and it's pretty nice. Another thing that's done, so diabetes is a disease that affects sugar regulation. So this is an example of a PET image of the foot of a patient with diabetes. So again, I'm not a medical doctor, I won't pretend I know exactly what's going on here. But it's one way, it gives doctors another tool to study the diseases that they're trying to study, to diagnose and to treat some of the diseases that their patients are faced with. And one of the nice things about PET is, from the previous image, you see the structure of the body. You can see bones. X-rays give you the structure of bones and stuff. But with these scans, because you're tracking molecules, you're actually able to track the function of things going on inside the body. Sometimes you can do this in real time, and you can look at where particular molecules are going through the body. I think I might have one more image. Yeah, so this is some stuff that's being done here at TRIUMF, actually. So this is a rat. This is one rat. This is another rat. They all have a particular type of tumor that's been implanted in them, and the isotopes that we're developing here are being used in tracers that are helping diagnose types of tumors that are actually very hard to diagnose using traditional methods that we know today. So this particular type of tumor is not the type of tumor that you can easily detect using those sugar scans that I showed you. It grows very, very slowly, so it actually doesn't use a lot more energy than the surrounding tissue, so it's hard to detect. But we're helping develop tracers that, over the course of 1 to 5 days, can actually get that tracer to be taken up by the tumor so that we can actually see it and make a diagnosis. So I think that's kind of cool. And yeah, not much to look at, but this is the cyclotron. So there's a particle accelerator here at TRIUMF where we actually produce these radioactive atoms that we're using for these diagnostic PET scans. And actually, UBC Hospital has some PET scanners. We produce the isotopes here on site. We do all the chemistry here on site. And then we have a pneumatic line that goes up Westbrook Mall. So we shoot these radioactive tracers up under the street to UBC Hospital, where there's a patient literally waiting in the PET scanner room, and the tube goes, and so when a technician takes itself out, injects it into the patient, they go into the scanner. And that's how some of the research and some of the stuff that we're doing here on Antimatter is actually being used every day by patients up at UBC Hospital to diagnose and follow the progression of things like cancer. So I think that's kind of cool. And that's the end of my field.